This is a problem from section 4.7 of the book, the section on applied optimization. The problem says that you have 40 meters of straight fence and you want to build a rectangular enclosure using 80 additional meters of fence, and that part of the fence can be bent. And we want it to encompass the greatest area. It says let A of x be the area of the enclosure with x as in figure 28. And so if you look at this figure, sorry, it's not the best picture. X is this little length beyond 40 that one of the side lengths is. So this red line is that 40 meters of straight fence, and the blue dotted line represents the 80 additional meters of fence that we have. And the problem, part A, says find the maximum value of A of x, so find the maximum area we can enclose. And part B says what interval is relevant to our problem and find the maximum value of A of x on this interval. Okay, so let's see. We know that A of x is the area of this rectangle in the figure. And the area of this rectangle is 20 minus x, the height, times the length, which is 40 plus x. And maybe I'll expand this out. It's a little easier to take the derivative that way. So we'll see, plus 20x minus 40x, so minus 20x minus x. So the area that's enclosed is 800 minus 20x minus x squared. And if you look at the figure, they've already taken into account that the blue line should, the blue dotted line should have length 80 meters. X plus 20 minus x is 20, plus 40 minus x is 60, plus x plus 20 minus x, that's 80. So that all works out. We don't need to take that into account. They already did it for us in the picture. Okay, so part A just says, let's maximize this value of A of x. So what we'll do for that is we'll take the derivative to find the critical points. And we'll get negative 20 minus 2x. So our critical point occurs at x equals, so to make sure I get the sign right, negative 10. And let's see, the maximum value, well, let's test it out. Oh, sorry, I meant A of negative 10. If we plug in negative 10, we'll get 20 plus 10 times 40 minus 10, using the original A of x equation that we had, which is 30 squared, which is 900. Okay, and if we think about it, if we take the limit as x goes to infinity of A, well, we'll get negative infinity, right? Because we have 800 minus something that's very large, minus another thing that's very, very large. So as x goes to infinity, A goes to infinity, A goes to negative infinity, excuse me. And also if we took the limit as x goes to minus infinity, we'll also get minus infinity. So this tells us that we have this one critical point, and as we go out to the positive infinity direction or the negative infinity direction, our function just goes to negative infinity. So we have something that looks like this parabola with this one maximum point. So A of x is maximized when x equals negative 10, and that maximum value is 900 square meters. Okay, so that was part A. The maximum value of A of x is 900 square meters. All right. But now for part B, they say, on what interval of x values should we actually have been maximizing A, right? Does it make sense that x is negative 10? Well, no, it doesn't. X has to be greater than or equal to 0. So let me erase this to give us some space for part B. Okay, so for part B, so yeah, so the smallest x can be is 0, and it could be 0. And what's the biggest that x could be? Well, the biggest that x can be, I guess, is 80. We won't actually enclose any area if x is equal to 80, but we could just lay our fence out in a straight line. Oops, that should be closed. Okay, so that's our relevant interval, and we saw from part A that there are actually no critical points. There are no critical points in this interval. Our only critical point was at x equals negative 10. So if we want to find the maximum on this interval, we should just test these endpoints. Now we're maximizing over a closed interval again. So let's see, a of 0, that was equal to 20 minus 0 times 40 plus 0, and that is, let's see, 20 times 40, that's 800. And a of 80, that's 20 minus 80 times 40 plus 80, and that turns out to be something negative, which really doesn't make sense. But it's because we didn't actually enclose any area with our 80. So, so our maximum value is 800. And if you wanted to be really, really sure that 800 were the maximum, you could test that. Remember that the derivative of a prime was negative 20 minus 2x, I think. And for x in our range, a prime is negative. So our function is decreasing on this whole interval. That tells us that the maximum must have occurred at the left endpoint before we had a chance to do any decreasing at all. So the max value of a of x is 800 square meters, I guess I should say, and that happens when x is 0.